Good morning, class. This recording is continuing from November 12th, lecture from last Thursday. And at that lecture, we focus on this particular file. You can find from the Canvas, named as Final Exam Information, and you can review plus finish chapter 15. The file itself finished the electrochemical analytical chemistry, and we finished chapter 14 and 15 in that particular file, and the recording you can see in the highlight in the yellow. What we'd like to do today in this recording is finish the remaining of chapter 16, and that will be 16-1 and 16-2. So if you load that particular file as a highlight here now with a star, and you can follow the lecture properly. Before we go into another reminder to you, the final exam will be on Canvas December 10 from 8 to 10 a.m. It will be comprehensive final exam, all multiple choice, and 60% will be from chapter 1 to 12, and that means it's from coverage with exam 1 and 2. 40% for new materials. Among the 40%, 25% of them will come from electroanalytical chemistry, and that is covered in chapter 14, 15, and now the remaining of 16-1 and 16-2. And finally, you have 50% of spectroscopy and separation science, and that will be covered after we finish this. And this is the coverage, how it look like. Now, we have done review in a previous recording of chapter 14 and then finish chapter 15 completely. So right now, we're going to take it over into the 16-1 and 16-2. And here, we will discuss about the shape of the redox titration curve and how to finding the endpoint and do the endpoint indicator. And this is covered in page 374 to 381. So by leaving the scope of chapter 16, I hope this is going to ease your final exam preparation. And I also add extra 0.5 point of bonus of chapter 16 homework assignments. And those homework assignment is 1, 2, 3, 4, and 6, 7, as showing up right here. And that will be due November 28th. Now, previously, at the end of chapter 14, we described how the electrochemical cell can operate with a redox reaction like this. So here we have a redox reaction. It has a cerium plus 4 and will be oxidizing iron 2 to iron 3, and cerium by itself reduced become the cerium plus 3. So how are we going to be able to use this particular redox reaction? Redox means reduction oxidation reaction, and draw electrochemical cell diagram and understanding how it look like. And one step further, how can we calculate some of the potential come from non-standard conditions shown right here? Because now you have 0.1, 0.5, 0.2, 0.3. Those are non-standard condition is deviate from the activity of 1. So a couple of questions coming out. What potential look up from table? And in this case, you will have to look up for the cerium 3, cerium 4 redox couple, and iron 2, iron 3 redox couple. And we're going to give you that information soon, but let's just go through the question together. What is the line rotation of a complete EChem cell look like based on that particular redox reaction? Then what electrode to use? What electrical potential can we use to describe this redox reaction, especially under non-standard condition? And with this particular cell setup look like this, the line rotation, then what will be the potential is positive, therefore we call galvanic cell, or is negative, that's means called electrolytic cell require energy to carry out those kind of specific reaction. Finally, if two half cells reach equilibrium, what will be the chemical equilibrium constants? And this is pretty much covered in the chapter 14 and 15. And here's I give you a summarize what it look like. Okay, so here give you what are the key components of understanding that you should know from previous discussions, and that correspond to all those answers. And here give you the list of the knowledge base that you need to know. But go straight into the cell itself. Okay, so now you can see where to look up the potential from your standard redox potential. You can find out iron 3, iron 2 is 0.767. And you can find out cerium 4 positive reduced to give cerium 3 positive. The standard reduction potential is 1.7. So that means, in this case, compare those two, that means that the cerium will stay in reduction because this is much higher positive, right? Much larger positive. And this will have to be reversed. And that's exactly what happened. Reverse means instead of in the reduction mode, you had to force to do an oxidation mode. And that is showing up in the end reactions. And we usually see is a cerium 4 positive plus the iron 2 give you cerium 3 positive and the iron 3 positive. Okay? So that's the potential you're looking for. And what about cell potential? It is the standard cell potential with 0 right here, indicating that the standard potential will be 1.70 minus 0.767 coming from that. Because this will have to be reversed. So therefore, the negative sign comes in. So you have a net potential of 0.933, and that is reading right here. And the 0.933, one can plug in this particular equation. This equation correlate equilibrium constants and standard cell potential. So after you do that, the calculation is 10 to the 17. So this is highly favorable, very favorable to the right here. You see, this is highly favorable to go to the right. Okay. Now, with those understanding of a potential, and now we go into here. So now you will see what happening here is where is NO? NO is the one get oxidized, so it had to be iron 2 and iron 3. Now, iron 2 and iron 3 redox reaction, it did not have a suitable electrode to use as the metal electrode. So we use platinum. Platinum as an indicator electrode allow us to indicating what kind of potential in this particular solution half cell. And that will be iron 3 and iron 2, right? So likewise, cerium 4 and cerium 3 on the right-hand side, it also did not have the potential to do that. So therefore, we need to have a platinum to go again as an indicator electrode to indicating what kind of potential going on right here. So in the cathode will be the cerium 4 positive plus electron give you cerium 3 positive. Cerium 3 positive. And NO itself, if you write the NO reductions, will be iron 2 become iron 3 and losing 1 electron. That's anonymous reaction going on here. Okay. So now this is those potential the potential here, standard potential, all in activity of 1. So if our cell become non-standard right here, you see right here, this is non-standard potentials. That means each one of those use a Nernst equation. Yeah, you require a Nernst equation right here. Require use of Nernst equations to do calculations. So one had to put the concentration of each species. For example, one had to use the iron 2 here on the top and then 3 on the bottom. In order to calculate the potential now for this anode, what would be the non-standard potential supposed to be? Okay, so that summarizes chapter 14 and 15 learning in this case. Whenever you want to use your Nernst equation, you always put the half cell reaction in the standard mode. That's mean reduction, in a reduction mode. So therefore, in order to put in the reduction mode, that you need to do it this way. So put it in the reduction mode. Put in reduction mode so you can plug in that equation to do your Nernst equation calculation. All right. Good. Now, we're going to move on now to, so we have just done a moment ago, we show you a review about what is the electrochemical cell, galvanic cell look like. And when the potential is less than 0, that means your delta G will be negative. So reaction will go spontaneous, will be spontaneous for carry out. So that's what this can behave as a battery. So what a battery means is when you connect the two cells together, the electron will keep flowing from one end to another end, from the anode side to the cathode side. Those electrons keep flowing until the battery complete discharge. The anode and cathode potential are equal to each other, and that you have the discharge battery. Okay, but what we're doing here in the redox titrations, our aim is to find out the analyte concentration. Find out the analyte concentration. We're not aiming to find out the voltage, what kind of voltage you got, what kind of battery performance. We're looking for the analyte. So as you can see on the right-hand side here, we utilize a titrant, highly oxidized titrant, to titrate with analyte. In this case, we're looking for the iron 2. So here, our iron 2 here is our unknown. We want to find out what is the iron 2 concentration look like. Although we know how it looks right now, because this is just a simulated situation, but in real application, this will be our unknown, okay? So, in order to do this particular titration, we rely on the redox titrations. We use a strong oxidized agent of cerium-4 and gradually drop in by burettes, drop by drop. Do we carry out a titration? So we know from previous discussion, this K value is very big. So whenever you drop in, you make a stirring, magnetic stirring, and then the reaction will be completed. So then, how that reaction get taking place right here, okay? How this is get monitored. And in that case is redox titration, we aiming to find out what is analyte. But therefore, what we do here, we remove all the boundary from the two half cell reaction. We kind of mix them together. So that no longer has any boundary. We have short battery. So everything is shorted together. Not aiming to generate electricity, aiming to carry out this reaction to the completion, so we can use that reaction to do our analytes, in this case iron 2 determination. So we're going to explain a bit further in the next view graph here. So before we go there, then if you mix everything together, previously you have a phase boundary. The phase boundary now removed, right? So everything mixed together, you have a shorter battery, and that means every time your your potential between those two, pardon me. Let's see, I need to go back. All right, the potential between these two half cells is always the same. Those two half cells is always the same because it's just shorted. And how you measure those potential? And the trick here is, one, again, use a plotting electrode, showing it right here, to indicating whatever solution in the potential here you are measuring, and measuring with respect to a standard column electrodes. So just like previously, when you're doing the acid-base titration, what you use to monitor them, you use a pH electrode, right? Okay, likewise, in this case, we're doing the redox titration. What we use to monitor, we use a platinum electrode as an indicator electrode to find out what are the solution redox potential look like. And platinum electrode cannot be standalone. It requires a reference. So we can always have to measure with reference electrodes. That's what, as far as this particular cell concerned, as you see in this particular block, the cell concerned right here, we are measuring in the beaker what the potential look like, use an indicator electrode and measure against the SCE, that's a reference electrode. Okay, now let's go a bit further here now. So titrations is a rapid reactions. It always in equilibriums. Every species mix them together, and because it has really a high equilibrium constant, so it reaches equilibrium very quickly. And platinum electrode monitor the solution redox potentials, and each one of them equal to each half cell in the equilibrium. That means the potential showing up right here in the platinum surface is measuring the potential equal to the iron 2, iron 3 redox coupled potential showing up in the solution, and also equal to the cerium 4 positive, 3 positive, because everything is in equilibrium. This is a dead battery, everything in equilibrium. So all of those potential have to be equal, and we use a platinum electrode to measure that. Okay, that's all good. And the solution redox potential, E platinum, is measured by the platinum intake electrode with respect to standard column electrode with a potential meter. So that is a final cell configuration as we stated earlier. You're starting with SCE, and then you go into the solution, SCE, go into the solution, measure what we have, and then come back to platinum here. And that is a cell. This particular cell here is representing like this. And the potential measurement from this reading here become a platinum electron minus E SE. So we call it as an E system. This is the potential you measure, okay? Now, the E system is used to indicating potential measure from the potential metric measuring system. Is the same as E used in your textbook. So in your textbook, use E. I use E system to make it clear because too many years around. So the E system is specific point to what we're measuring right here from this particular meter. That's called E system. And the potential of our interest is right here. But the E platinum cannot be measured alone without compared to reference. So therefore, we have to rely on E system to measure in real time. Okay, so this is what the titration curve looks like. If we measure the E system with respect to the cerium 4 LAN, you see a very familiar shape of a curve going on here. And there's one period of time you have a potential go up and down very, very sharply. And in the middle of this, where your endpoint is supposed to be. And we're looking at this particular endpoint volume. And if you know the concentration of your cerium, indeed we know. Then you can find out what is the concentration of your unknown. Again, this is always the same, right? With the endpoint, based on your titrant concentration, now you can find out what is your analyte concentration supposed to be. So all the time, when we do those kind of titration work, we are monitoring the E system with respect to the volume of titrant, that is oxidizing agent. Now let's get into calculations. So review what is the key concept. All the potential is equal to the half cell potential. This is always in equilibrium right here. Those are always in equilibrium. And the system potential from this system we measure here, it is a platinum potential minus the reference electrodes. Okay. And the reaction is always what in the burette react with what in the beaker. So what in the burette is what in the beaker, and this is the end result. Turn out in this case, you have a 1-to-1 ratio, the stoichiometric ratio. So it will be N times V of titrant versus N times V of analyte equal to 1-to-1. So by easily plugging those information you get from here and that from there, okay, you'll find out what will be the, you can find out what will be the endpoint supposed to be. So endpoint supposed to be 50, okay? So before the endpoint, this endpoint 50. Before the endpoint, we use the E system from the one left over from the iron 2 and iron 3 redox couple. Whatever left over, we will use that one to do calculation because it's much easier to do that way. All right, so let's see. If you have at the midpoint, that's 25 right here. So that where your 25 milliliter. So in the 25 milliliter here, what will be the potential look like? And you know, at the 25, that means we have 50% of reaction completed, right? So therefore, you know, the 50% reaction completed. So therefore, only 50% of them move over here. So this is 50% and this is 50%. So they are equal amount. So we know if you base on the Nernst equation coming out from the iron 2 and 3 redox couple. So then this will be the standard potential coming from iron 2 and 3. So this will be E naught, iron 2 and 3. So this is 0.767 is coming from that. And you minus 0.05916 divided by 1 because there's 1 electron transfer for this particular redox couple. Since iron 3 plus 1 electron give you iron 2. So you only have 1 electron. So they divide by 1. So that we don't need to write it here very clearly. So you plug everything in, you find out, oh, the potentials for the platinum potential is 0.767. But important, this is not E system. Okay. This is not E system yet. That is not E system. E platinum is not equal to E system because E system will require is the platinum potential measured with respect to the standard Kalman electrodes. Platinum potential with respect to standard Kalman electrodes. So we still have to, with this calculation, E platinum minus 0.241 SE, then give you this particular potential. That would be E system. That's exactly what you have here. That would be E system. Because that is a potential we can measure from this meter. And that potential here, E platinum, is just that platinum electrode. We need to measure with respect to something. And that that particular measurement we measure with respect is measured with respect to standard carbon electrodes. Okay, go a bit further. How about I move from 25 now to 36? Okay, again, it's very simple. Just do your stoichiometry accounting, right? So you're starting with this much in the beaker, and you adding this much as your oxidation reagent, cerium 4 parts as your titrant. You know this is before the endpoint, before endpoint 50. So therefore, this has to be limiting, meaning is you will use up completely, exactly right here, use up completely, and how much leftover will be 5 minus 3.6 millimole, and how much you're making will be 3.6 millimole. So in this case, you can tell which redox couple readily available, which redox couple readily available is this one, iron 2 and iron 3 before the endpoint, right? Because you see a number here easy to find, and this number will take some effort to find out, okay? So we use iron 2, iron 3 in this case. That is the one easy to find, so we use that. Again, instead of 1-to-1 previously, now we have different ratio now. And so we plug in a different ratio. You could calculate. Again, we have to measure with respect to SCE because we need to see the E system potential. So 0.455550. So that's, I see here, this point is that one. Okay. Excellent. All right. You can use that particular cerium 4 positive and 3 positive to do a calculation, but you're going to take a lot of work. So you're going to get the same result if you use this, okay? But it would be better to use the one readily available, okay? You can use this is okay, but it's going to take a lot of effort. Use this already available. This will be much easier and save time. And that's why we do here. Because after all, this is the dead battery. So the potential for two different redox couple will be always the same. You can choose whichever you want to do. Now we reach the endpoint. By adding the 50 milliliters in the solution now we have exact equal the titrant to analyte. So those two are exactly equal to one another. Consequently, they are annihilate one another, so complete oxidize, and therefore this becomes 0, 0, and that you have product coming on the right hand side. So you know, when you reach equivalence point, you're adding exactly the amount required to oxidize whatever you have of iron 2 in the beaker. Now you have a situation that in the product side they are equal, and in the reactant side they are equal. Okay, so if you use this and plug into the Nernst equation for each one of those half-cell reaction, iron 2, 3, and cerium 3 and 4, if you add it together, you plug in those relationships here, you'll find out the cerium 4 and cerium 4 and the iron 2 can't cancel out because that comes from that relationship. And this also cancel out coming from that relationship. So the end result is now your platinum potential at the equivalence point become 1/2 of half cell potential of two different redox couple adding together. So become 0.767 plus 1.7 divided by 2. And your endpoint platinum potential, electron potential is 1.23. Again, we have to convert it to the system potential we actually can measure from this particular meter, and that had to measure with respect to the SCE, and therefore it's 0.99 per SC. And that is exactly what we see in here. That is 0.99 volt. See, burst SCE. Okay, so the end result here is if you have 1-to-1 ratio, your endpoint potential, observing by a plotting electrode is equal to 1/2 of individual standard potential divided by 2. So it does happen to be that way. Now, if you have some redox couple becomes 3A plus 3C is now 1-to-1, this is no longer a whole, okay? The reaction, to, let's say B, 2A, 3B to C and plus D. If you have the ratio is now 1-to-1, it cannot be just added together divided by 2. Please look at your textbook itself. It will give you more detailed explanation how this will work. Okay, now we pass the endpoint. Let's say 50 milliliters endpoint. Let's look at what a 63 look like. Okay, so in a 63 milliliter, we know which gonna be limiting. Whatever in your beaker itself will be limiting. Okay, because we already use the excess of a titrant. So that means this will close to 0, and then you're creating corresponding how much you have right here. So now you see which is left over. The ion 2 and 3 no longer easy. The leftover one is Syrian 3 and 4, because you can find Syrian 3 here easily, that's why you can find a Syrian 4 easily, whatever left over here. So now you switch from ion 2 and ion 3 easily used before equivalence point. Past equivalence point, the easily used one is Syrian 3, 4 and 3 positive. So therefore we use that. Plug in the proper number, calculate what is the platinum potential look like, and then with respect to SCE, now your system potential was supposed to be, and that exactly right here. Okay, so after we know these important concepts, that the potential of platinum is layered to measure the depth battery, meaning when you do your redox titration, you reach the compression. Both redox couple will always their potential will always equilibrium. That means their potential always equal, and then you can use the system of the platinum electrode minus whatever SCE look like, and based on that particular system to measure it. And if you know how to do it, and choose the right redox couple, and you can handle the redox titration equation, not a problem. Okay. Finally, how to find the endpoint? Again, for each of those SCM base or ETDA titration, likewise, we have a redox indicator. They can change color with going from the oxidized to the reducting states. That means when some of the indicator, like this ferrium, in a reduced state, it look like blue. In the oxidized state, it look like red. And what potential it will change from the blue to red is somewhere around 1.147 volt versus standard hydrogen electrode. Okay, this is with respect to the standard hydrogen electrode. So in this case here, it will allow you to see you can starting from oxidized state, and reducing states, go into oxidized state, it will changing color. And that color transition right here is where it become useful for you to find out what will be the endpoint supposed to be. Okay, let's see how it works. Huh? Okay, so you see, like here, this is what all the color look like. And the one example we are focused on, we are focused on right here now. Focus on here is the ferrium. Okay, all right. I will get it back again. Okay, sorry for interruption. So we're back again. So now let's go to the next. So all those potential here indicating about what are the indicator look like. Oh, unfortunately, we had that problem. Okay, so all those potential indicating, or each one of those redox indicator, what kind of potential they were changing color. So here, give you an example, right? If you focus on ferrium, and the ferrium itself, that potential is with respect to standard hydrogen electrode. So everything we are measuring right here, we will have to respect to SCE. So if you do comparing this potential burst SCE, you see you are changing color in this particular domain. So then if you plug in right here, you see this will be ferrium will be the one most close to the endpoint potential. So it will allow you to see from the reduction to oxidizing state, they're going to see color change, and the potential you see a color change will be fitting just right. Now, if you comparison, if you use something else right here, this particular uh, uh, indicator, then you will have an error because you are changing color too early. Okay. All right. And lastly, sometimes we use the starch as an indicator because you were changing color with a very blue color. And the remaining of the chapter 16 give you a lot of different application example that use different type of oxidants to do the titration. You know, it could be iodate, iodize, and also could be perchlorate and permanganase. And those have a rich chemistry to describe how you apply in the industrial situation. And although I'm not going to test that, so if you are curious and you have extra time, you should go to read them. The chapter 16 is quite useful at the end. But anything up to chapter 16-2 that you will not be tested for the final exam in order to ease your workload, okay? All right, so this is ended, conclude our coverage for electroanalytical chemistry, chapter 14, 15, and 16-1 and 16-2. And this will be covered by final exam with 25% of the questions. And so that you can prepare accordingly. Okay, so this recording will end here. We're gonna go to the next section. It will cover the spectrophotometry. That is using the light to do the analytical purpose characterization. Okay, take care.